Many Worlds retains locality at the level of the Schrödinger equation, but redefines what is meant by a single outcome. Entanglement is universal and never undone. Independence between branches emerges only through decoherence. A third approach, originally proposed by David Bohm in 1952, takes yet another path. Bohmian mechanics, sometimes called pilot wave theory, introduces definite particle positions guided by a wave function. In this framework, particles always possess precise positions. The wave function evolves according to the Schrödinger equation and influences particle motion through what Bohm called the quantum potential. The guidance equation can be written in words as the velocity of a particle equals Planck's constant, divided by mass multiplied by the imaginary part of the gradient of the wave function, divided by the wave function. This guidance relation ensures that particle trajectories reproduce quantum predictions when initial positions are distributed according to the Born rule. Entanglement in Bohmian mechanics manifests as non-local guidance. The wave function of a composite system lives in configuration space, not ordinary three-dimensional space. As a result, the motion of one particle can depend instantaneously on the configuration of another distant particle through the shared wave function. Basil Hiley and others have further developed this framework, exploring its implications for quantum field theory and information. Bohmian mechanics preserves realism in the sense that particles have definite positions, but it sacrifices locality at the fundamental level. It is explicitly non-local, though still constructed to avoid faster-than-light signaling at the level of observable phenomena. Another interpretation, more recent and philosophically distinct, is cubism, short for quantum Bayesianism. Christopher Fuchs and collaborators have advanced this view. Cubism treats the quantum state not as a description of objective reality, but as a representation of an individual agent's degrees of belief about future experiences. In cubism, probabilities are personal and Bayesian. The Born rule is interpreted as a normative rule guiding how agents should update their expectations in light of possible actions and experiences. Entanglement does not represent a mysterious physical bond across space. It encodes an agent's expectations about correlations between experiences resulting from measurements. Cubism does not deny the existence of an external world. Rather, it reframes quantum theory as a tool for agents interacting with that world. The wave function does not exist independently in space. It exists in the agent's bookkeeping of probabilities. This approach avoids ontological extravagance and non-local hidden variables, but it shifts the focus toward experience and information. Across these interpretations, the empirical predictions remain identical. All reproduce the Born rule. All agree on the violation of Bell inequalities. All predict decoherence and its consequences. No currently known experiment distinguishes decisively among them. The differences lie in ontology and explanatory style. Copenhagen emphasizes measurement and classical description. Many Worlds embraces universal entanglement and branching structure. Bohmian mechanics restores definite trajectories at the cost of explicit non-locality. Cubism recasts the wave function as an agent-centered tool for managing expectations. Each interpretation must account for entanglement. None can deny it. They disagree on what it represents. Does entanglement reflect a branching multiverse, a non-local guiding field, an update in knowledge, or a structure in an agent's probabilistic expectations? The mathematics remains unchanged. The physical predictions remain the same. This situation is unusual in science. In most areas, competing theories make different empirical claims. Here, interpretation operates at a different level. It concerns what the formalism means rather than what it predicts. For many working physicists, this plurality is tolerable. The equations work. The experiments agree. Technologies such as quantum cryptography and quantum computing proceed without needing to settle the ontology. Yet the interpretational debate continues because entanglement challenges deep intuitions about independence, locality, and reality. Perhaps the most important point is this: regardless of interpretation, Entanglement is not an optional extra. It is embedded in the mathematical structure of quantum theory. Any interpretation must explain why composite systems are described by non-factorizable states, and why Bell inequalities are violated. The interpretations differ in how they describe what exists beneath or alongside that structure. They do not differ in how nature behaves in the laboratory. In that sense, entanglement is experimentally settled but conceptually open. It anchors the theory empirically while leaving space for philosophical exploration. And in that quiet space between equation and meaning, the deeper implications of quantum structure continue to unfold. So far, entanglement has often been described in terms of particles, two photons emitted from the same source, two spins prepared in a singlet state, pairs of systems that interact and then separate. But modern physics does not treat particles as the most fundamental entities. The deeper framework is quantum field theory. In this description, the basic ingredients of nature are fields that extend throughout space and time. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks arise from quark fields. Even what appears as empty space is filled with quantum fields. Within this framework, entanglement is not something added later when two particles collide. It is woven into the structure of the fields themselves. One mathematically rigorous approach to quantum field theory is known as algebraic quantum field theory. Rudolf Hegg played a central role in developing this formulation in the 1950s and 1960s. Instead of focusing primarily on particle states, algebraic quantum field theory emphasizes local algebras of observables assigned to regions of spacetime. In this approach, each spacetime region is associated with a set of operators representing measurable quantities within that region. These local algebras satisfy precise mathematical properties, including locality conditions. Observables associated with space-like separated regions commute, ensuring compatibility with special relativity. What is striking is that even in the vacuum state, the lowest energy state of the field with no particles present, there is entanglement between different regions of space. This idea can feel counterintuitive. Vacuum suggests emptiness. Yet in quantum field theory, the vacuum is not a simple void. It is a highly structured state, with fluctuations arising from the uncertainty principle. If one divides space into two regions separated by a boundary, the vacuum state of the quantum field does not factorize into a simple product of a vacuum for region A and a vacuum for region B. Instead, the global vacuum is entangled across the boundary. This is not a speculative claim. It follows from the mathematical structure of quantum fields and has been explored rigorously in algebraic quantum field theory. A particularly deep result in this context is the Rie-Schlieder theorem. Named after Helmut Rie and Siegfried Schlieder, this theorem states, roughly speaking, that by applying local operators within any non-trivial region of spacetime to the vacuum state, one can approximate any state in the Hilbert space arbitrarily well. Conceptually, this means that the vacuum is highly entangled across space-like regions. Local operations in one region have access in principle to the full richness of the global state. This does not imply faster-than-light signaling. The commutation of observables in space-like separated regions still guarantees that local measurements cannot transmit information superluminally. Instead, the theorem highlights the depth of entanglement embedded in the vacuum itself. The vacuum is not a simple, separable background. It is a globally correlated state. Another remarkable consequence of quantum field theory in curved or accelerated frames is the Unruh effect, predicted by William Unruh in 1976. According to the Unruh effect, an observer undergoing constant acceleration will perceive the vacuum as a thermal bath of particles. In other words, what an inertial observer describes as empty space appears warm to an accelerating observer. The temperature associated with this effect is proportional to the acceleration. In everyday units, the acceleration required to produce even a tiny temperature is enormous, far beyond ordinary experience. Nevertheless, the theoretical prediction arises directly from the structure of quantum fields and their entanglement across spacetime regions. The Unruh effect reflects how the vacuum state is entangled between different modes defined relative to different observers. When one restricts attention to a subset of spacetime accessible to an accelerating observer, the reduced state appears thermal. The apparent temperature arises from tracing out inaccessible degrees of freedom beyond the observer's horizon. This phenomenon parallels ideas in black hole physics. Stephen Hawking showed in 1974 that black holes radiate thermally due to quantum effects near the event horizon. The Hawking radiation process can also be understood in terms of entanglement between modes inside and outside the horizon. These examples demonstrate that entanglement in quantum field theory is not limited to carefully prepared laboratory systems. It is a pervasive feature of the vacuum and of spacetime itself. In ordinary particle physics experiments such as those conducted at the Large Hadron Collider at CERN, entanglement appears routinely in scattering processes and decay products. When particles are created in high-energy collisions, conservation laws often enforce correlated properties, such as total spin or momentum. The resulting states are entangled by construction. Yet even before any collision occurs, the fields filling space are already entangled across regions. This shifts the perspective once again. Entanglement is not an anomaly produced by special preparation. It is the natural state of quantum fields. In algebraic quantum field theory, the assignment of local algebras to regions highlights a tension between locality of observables and global entanglement of states. Observables in space-like separated regions commute, preserving relativistic causality. At the same time, the global state, including the vacuum, may be highly entangled. The structure is subtle but consistent. Local measurements cannot influence distant outcomes in a way that violates special relativity. Yet the statistical correlations between regions reflect a shared global structure. The independence of distant regions, assumed in classical field theory, no longer holds at the level of quantum states. Instead, the vacuum itself encodes correlations across space. One way to visualize this is to imagine dividing space into two halves. Even if no particles are present, the quantum field in one half cannot be described independently of the field in the other half. The global vacuum state contains correlations that link them. This entanglement has measurable consequences. In condensed matter physics, similar ideas lead to the concept of entanglement entropy, which quantifies how much entanglement exists between regions. In quantum field theory, entanglement entropy typically scales with the area of the boundary, separating regions rather than their volume. This area law behavior has deep connections to gravitational physics and the holographic principle. The central message is steady and clear. Entanglement is not an optional add-on to quantum theory. It is embedded in the fabric of quantum fields. It persists even in what appears to be empty space. It respects relativistic causality while reshaping the notion of separability. Particles may come and go. Fields fluctuate. Observers move inertially or accelerate. Throughout it all, the underlying structure remains entangled, and once entanglement is recognized as intrinsic to the vacuum and to spacetime regions themselves, the question of connection becomes even more profound. The links between distant regions are not imposed from outside. They arise from the fundamental architecture of quantum field theory. What once seemed like a peculiar feature of specially prepared particle pairs becomes, at this level, a pervasive aspect of the quantum world itself. Entropy began as a measure of heat and disorder. In the 19th century, Ludwig Boltzmann connected thermodynamics to microscopic physics by proposing that entropy reflects the number of microscopic configurations consistent with a macroscopic state. His famous formula, engraved on his tombstone in Vienna, can be written in words as entropy equals Boltzmann's constant, multiplied by the natural logarithm of the number of microstates. That equation expresses a powerful idea. When many microscopic arrangements correspond to the same large-scale description, entropy is high. When only a few arrangements are compatible, entropy is low. In classical statistical mechanics, entropy quantifies ignorance about the exact microscopic state. A gas in a box contains an enormous number of molecules, each with its own position and velocity. It would be impractical to specify all of them individually. Instead, one describes macroscopic quantities such as temperature and pressure. The entropy reflects the number of microscopic arrangements that give rise to those macroscopic values. Quantum mechanics reframes this picture. John von Neumann generalized the concept of entropy to quantum systems. Instead of counting classical microstates, he defined entropy in terms of the density matrix, a mathematical object that encodes probabilities for quantum states. The von Neumann entropy is written in words as entropy equals minus the trace of the density matrix multiplied by the natural logarithm of the density matrix. Although that expression may sound abstract, its meaning parallels Boltzmann's idea. If a quantum system is in a pure state, meaning it is described by a single state vector with complete coherence, its von Neumann entropy is zero. There is no uncertainty about the state. If the system is in a mixed state, representing a statistical mixture of possibilities, the entropy is greater than zero. The density matrix formalism is especially useful when dealing with subsystems of a larger entangled whole. Suppose two systems are entangled and described by a joint pure state. The composite system may have zero von Neumann entropy. However, if one focuses only on one subsystem and traces out the other, the reduced density matrix typically describes a mixed state. This reduced state carries non-zero entropy. The entropy is called entanglement entropy, when it arises purely from tracing out part of an entangled system. It measures how strongly the subsystem is correlated with the rest of the system. To understand this intuitively, imagine two qubits prepared in a maximally entangled state. The joint system is in a pure state. Yet if one examines only one qubit, its reduced density matrix assigns equal probability to two outcomes. The single qubit appears completely random. Its entropy is maximal. The randomness does not reflect ignorance about a hidden variable. It reflects entanglement with the other qubit. Entanglement entropy therefore quantifies how information is distributed across subsystems. This concept connects directly to Boltzmann's statistical mechanics. In classical thermodynamics, entropy often increases because microscopic correlations become inaccessible. In quantum mechanics, entanglement spreads correlations across degrees of freedom. When a subsystem is considered in isolation, its entropy increases as it becomes entangled with its environment. Decoherence, discussed earlier, can be described in these terms. As a system interacts with its environment, entanglement entropy between them grows. The reduced state of the system becomes mixed. Interference terms fade. Classical probabilities emerge. This is not entropy in the sense of disorder alone. It is entropy as a measure of quantum correlation. The idea that entanglement distributes information rather than destroying it is central. When two systems become entangled, information about one system is encoded in correlations with the other. The joint state retains coherence, but the local description appears uncertain. In many body physics, entanglement entropy has become a powerful diagnostic tool. Researchers studying quantum phase transitions examine how entanglement entropy scales with system size. In one-dimensional systems with short-range interactions, ground states often obey an area law. The entanglement entropy between a region and its complement scales, with the boundary between them rather than the volume of the region. This is surprising from a classical perspective. Classical correlations typically scale with volume. Quantum entanglement, however, often scales with area. This area scaling appears not only in condensed matter systems, but also in quantum field theory, as mentioned earlier. When space is divided into two regions, the entanglement entropy of the vacuum typically scales with the area of the boundary separating them. Such scaling hints at a deep connection between entanglement and geometry. Before reaching geometry, it is helpful to emphasize the informational perspective. In classical information theory, developed by Claude Shannon in 1948, entropy measures the average uncertainty of a random variable. Shannon entropy is defined in words as entropy equals minus the sum over probabilities of probability multiplied by the natural logarithm of probability. Von Neumann entropy generalizes this to quantum systems. When the density matrix is diagonal in some basis, the von Neumann entropy reduces to Shannon entropy for the corresponding probability distribution. Entanglement entropy, therefore, can be interpreted as a measure of how much information about one subsystem is encoded non-locally in correlations with another. This viewpoint aligns with developments in quantum information science. Entanglement is treated as a resource. It enables quantum teleportation, superdense coding, and certain computational speedups. These protocols rely on the distribution of information across subsystems in ways impossible for classical systems. Consider quantum teleportation, first proposed by Charles Bennett and colleagues in 1993. Teleportation does not transmit matter or energy instantaneously. Instead, it transfers quantum information using shared entanglement and classical communication. The success of the protocol depends on the entanglement entropy between the participating systems. Entanglement entropy thus becomes a quantitative bridge between foundational physics and practical information processing. It also prepares the ground for deeper theoretical developments. In black hole physics, Jacob Bekenstein and Stephen Hawking discovered that black hole entropy is proportional to the area of the event horizon. This area law echoes the behavior of entanglement entropy in quantum field theory. Such parallels suggest that entropy and geometry may be intertwined more profoundly than classical thermodynamics anticipated. At this stage, a pattern emerges. Entanglement reshapes locality. It challenges separability. It underlies decoherence and classical appearance. It defines new forms of entropy. And it distributes information across subsystems in ways that classical correlations cannot replicate. The classical picture of independent parts, each carrying their own information, gives way to a network of correlations woven through quantum states. Entropy, once a measure of disorder in steam engines and gas cylinders, now measures the depth of quantum connection between regions of space and between subsystems of a field. And as entanglement entropy reveals its area-scaling behavior and its link to horizons and boundaries, a new possibility begins to take shape. Perhaps geometry itself, the structure of spacetime, is related to patterns of entanglement. That possibility lies just beyond the horizon of information theory, where quantum structure meets gravitational physics. In classical physics, geometry comes first. Space is a stage. Distances are measured by rulers. Angles are defined by straight lines. Matter moves within a pre-existing arena. Even in general relativity, where spacetime is dynamical and curved by mass and energy, geometry remains fundamental. The Einstein field equations state, in words, spacetime curvature equals 8π multiplied by the gravitational constant divided by the speed of light to the fourth power, multiplied by the stress energy tensor. Geometry responds to matter, but geometry itself is still a primary ingredient. In recent decades, a different possibility has gained attention. What if spacetime geometry is not fundamental? What if it emerges from patterns of quantum entanglement? This idea began to crystallize in the 1990s with the holographic principle, proposed independently by Gerard 't Hooft and later refined by Leonard Susskind. The inspiration came from black hole thermodynamics. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. Specifically, the entropy is proportional to the area divided by 4 times Planck length squared. The Planck length is an extraordinarily small scale, roughly 1.6 times 10 to the minus 35 meters. The appearance of area rather than volume suggested something profound. In ordinary systems, entropy scales with volume. More space usually means more degrees of freedom. Black holes defy this expectation. Their entropy scales with surface area. The holographic principle takes this observation seriously. It proposes that the information content of a region of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. If correct, this principle implies that the fundamental description of a volume of space might reside on its lower dimensional boundary. A dramatic realization of this idea came in 1997, when Juan Maldacena proposed the anti-de Sitter/conformal field theory correspondence, often called ADS/CFT. Maldacena suggested that a quantum theory of gravity defined in a higher dimensional spacetime with anti-de Sitter geometry is mathematically equivalent to a conformal field theory defined on its lower dimensional boundary. In simpler terms, physics in a curved spacetime with gravity can be equivalent to a quantum field theory without gravity living on the boundary of that spacetime. This correspondence is not a loose analogy. It is a precise mathematical duality supported by extensive calculations. In this framework, the extraspatial dimension of the gravitational theory emerges from properties of the boundary field theory. Entanglement plays a central role in this emergence. In 2006, Shinsei Ryu and Tadashi Takayanagi proposed a remarkable formula connecting entanglement entropy in the boundary theory to geometry in the bulk gravitational spacetime. The Ryu-Takayanagi formula states, in words, the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk spacetime divided by 4 times the gravitational constant. This formula echoes the black hole entropy relation. It ties a purely quantum information quantity, entanglement entropy, to a geometric area in a higher dimensional space. In the AD-CFT context, if one takes a region of the boundary conformal field theory and computes its entanglement entropy, that entropy corresponds to the area of a surface extending into the bulk anti-de Sitter space that is anchored on the boundary of the chosen region. Geometry appears to encode entanglement. The implication is extraordinary. The connectivity and curvature of spacetime in the bulk may reflect how strongly different regions of the boundary theory are entangled. If entanglement between boundary regions changes, the geometry of the bulk adjusts accordingly. In some scenarios, reducing entanglement between two regions of the boundary can cause the bulk spacetime connecting them to pinch off or disconnect. This line of thought suggests that spacetime itself might be woven from entanglement. Parallel insights have emerged from tensor network models developed in quantum many-body physics. Guillaume Vidal introduced the multiscale entanglement renormalization ansatz, commonly abbreviated as MIRA. MIRA is a tensor network designed to efficiently represent quantum states with specific entanglement structures, especially in systems near critical points. In a tensor network, the quantum state of a many-body system is represented as a network of interconnected tensors. The pattern of connections reflects how entanglement is distributed across scales. Remarkably, the geometry of certain tensor networks resembles the geometry of anti-de Sitter space. The hierarchical structure of MIRA, with layers corresponding to different length scales, mirrors the radial direction in ADS spacetime. Each layer in the network can be interpreted as encoding degrees of freedom at a different scale, similar to how the extra dimension in AD-CFT corresponds to energy scale in the boundary theory. This resemblance is not merely aesthetic, it reinforces the idea that geometric structure may arise from entanglement patterns. If quantum states can be represented as networks whose connectivity defines an emergent geometry, then geometry itself may not be fundamental. It may be a large-scale manifestation of quantum correlations. This perspective reframes earlier discussions about separability. Classical geometry assumes that points in space are distinct and separated by well-defined distances. If geometry emerges from entanglement, then distance itself may reflect how strongly subsystems are correlated. Two regions that are highly entangled might be considered close in the emergent geometry. Regions with little entanglement might be far apart. Leonard Susskind has described entanglement as the glue holding space-time together. This metaphor captures the intuition without overstating certainty. The precise mechanisms remain under investigation, but the mathematical connections are compelling. It's important to emphasize that these ideas are most rigorously developed in specific theoretical settings, particularly anti-de Sitter space. Our observable universe appears to have a positive cosmological constant rather than the negative curvature of anti-de Sitter geometry. Extending holographic ideas to realistic cosmology remains an active area of research. Nevertheless, the conceptual shift is clear. Entanglement is no longer viewed solely as a feature of particle pairs or laboratory systems. It may underpin the structure of space-time itself. The holographic principle suggests that information scales with area. The AD-CFT correspondence provides a concrete duality, linking gravitational geometry and quantum field theory. The Ryu-Takayanagi formula ties entanglement entropy directly to geometric surfaces. Tensor network models offer intuitive pictures of how entanglement patterns can generate spatial structure. Across these developments, a common theme appears. Geometry and entanglement are intertwined. The classical image of space-time as a fixed backdrop gives way to a more relational view. Space-time may emerge from the quantum state of underlying degrees of freedom. Distances and curvature could reflect patterns of correlation. If that is the case, then the earlier question about how distant things remain connected acquires a deeper layer. Perhaps distance itself is not fundamental. Perhaps what appears as spatial separation arises from the structure of entanglement in a more basic quantum description. These ideas remain at the frontier of theoretical physics. They are mathematically sophisticated and not yet confirmed by direct experiment in the context of quantum gravity. Yet they represent a serious and ongoing attempt to unify quantum theory with gravitational geometry. In this view, entanglement is not merely a curious quantum feature. It may be the scaffolding from which spacetime is built. And if spacetime geometry reflects entanglement structure, then the connection between distant regions is not an anomaly within space. It may be a hint about how space itself comes into being. In 1935, two seemingly separate ideas entered physics almost simultaneously. One was the Einstein-Podolsky-Rosen paper, questioning the completeness of quantum mechanics and highlighting entanglement. The other was a solution to Einstein's equations discovered by Albert Einstein and Nathan Rosen, describing what is now called an Einstein-Rosen bridge. At the time, these ideas were unrelated. One concerned quantum correlations. The other concerned space-time geometry and general relativity. Decades later, in 2013, Juan Maldacena and Leonard Susskind proposed a bold conjecture linking them. They suggested that ER equals EPR. In words, Einstein-Rosen bridges are equivalent to Einstein-Podolsky-Rosen entanglement. To unpack this, it helps to recall what an Einstein-Rosen bridge is. In general relativity, certain solutions to the Einstein field equations describe black holes. When extended mathematically, some of these solutions contain a structure connecting two asymptotically separate regions of spacetime. This structure resembles a tunnel or throat linking distant regions. It is often called a wormhole. The simplest such object is a non-traversable wormhole. It connects two regions geometrically, but no signal or object can pass through it from one side to the other. The throat pinches off too quickly, and any attempt to cross would encounter extreme gravitational effects. The key point is that an Einstein-Rosen bridge represents a topological connection in spacetime. Two regions that appear distant in ordinary space may be connected through a higher dimensional geometry. Maldacena and Susskind's conjecture proposes that certain entangled quantum states are equivalent, in a precise theoretical sense, to space-time geometries containing such bridges. In particular, they considered pairs of black holes prepared in a maximally entangled state. Within the anti-de Sitter/conformal field theory framework, such a pair can be described as two black holes connected by a non-traversable wormhole. The entanglement between the two systems corresponds to the geometric connection in the bulk spacetime. This idea does not suggest that entangled particles in a laboratory are literally connected by tiny traversable tunnels. Instead, it proposes a deep equivalence between quantum entanglement and geometric connectivity at a fundamental level. The slogan ER equals EPR captures this equivalence succinctly. ER stands for Einstein-Rosen bridge. EPR stands for Einstein-Podolsky-Rosen entanglement. The conjecture remains theoretical. It is grounded in the mathematical structure of holographic dualities, particularly within anti-de Sitter spacetime. It does not yet have direct empirical confirmation in our observable universe. Nonetheless, it builds on solid theoretical foundations. The anti-de Sitter/conformal field theory correspondence, proposed by Maldacena in 1997, provides a concrete setting in which gravitational geometry and quantum entanglement are mathematically linked. The Ryu-Takayanagi formula already connects entanglement entropy to minimal surface areas in the bulk. ER equals EPR extends this connection. It suggests that entanglement may be understood as a form of spacetime connectivity. It is essential to clarify what this does and does not mean. It does not mean that entanglement allows faster than light travel through wormholes. The Einstein-Rosen bridges considered in these models are non-traversable. No signal can pass through them. Causality remains intact. It does not mean that laboratory-scale entanglement experiments have revealed microscopic wormholes directly. The conjecture operates at a level of theoretical description within specific models of quantum gravity. What it does mean is that entanglement might have a geometric interpretation. Instead of thinking of entangled systems as mysteriously correlated across empty space, one might think of them as connected through a deeper topological structure in an underlying spacetime. In this view, distance and connectivity are not purely geometric primitives. They may arise from entanglement patterns. Topology, the mathematical study of connectedness and continuity, becomes central. Two regions of space that are far apart in ordinary coordinates might nonetheless be connected in a higher dimensional description. Conversely, reducing entanglement between regions might correspond to tearing or separating spacetime in the bulk geometry. These ideas are speculative but not arbitrary. They are motivated by consistent mathematical frameworks in string theory and holography. Researchers continue to explore how robust the ER equals EPR conjecture is beyond idealized anti-de Sitter settings. There are also intriguing links to quantum information. In some thought experiments, such as those involving black hole evaporation and the information paradox, entanglement structure plays a crucial role in maintaining consistency with unitarity and avoiding contradictions. The Hayden-Preskill thought experiment, for example, analyses how quickly information thrown into a black hole can be recovered from Hawking radiation under certain entanglement assumptions. These considerations reinforce the centrality of entanglement in gravitational contexts, yet caution is warranted. The ER equals EPR conjecture is not experimentally verified in the way Bell inequality violations are. It is part of an ongoing theoretical effort to unify quantum mechanics and general relativity. Its strength lies in the coherence of the mathematical structures involved. Holographic dualities, minimal surfaces, and entanglement entropy calculations all point toward a deep relationship between geometry and quantum correlations. What once appeared as a puzzling non-local correlation might be reinterpreted as a reflection of hidden connectivity in spacetime. If entanglement corresponds to geometric bridges, then the phrase distant things may require refinement. They may be distant according to one coordinate system, yet connected in another, more fundamental description. This does not eliminate the need for careful reasoning about causality and signaling. Non-traversable wormholes do not permit shortcuts for information transfer. The no-signaling theorem remains in force. Instead, the emphasis shifts from signaling to topology. Entanglement becomes less about instantaneous influence and more about shared structure. The universe, in this speculative but mathematically grounded picture, is not composed of isolated islands separated by empty void. It is a network of correlations whose geometry reflects those correlations. Whether this vision fully captures the nature of spacetime remains an open question. What is clear is that entanglement has moved from the margins of quantum theory to the heart of attempts to understand gravity and geometry. And in that movement, the idea of connection acquires a new meaning, not as a signal racing through space, but as a fundamental link in the architecture of reality itself. For much of the 20th century, quantum mechanics was viewed primarily as a theory about atoms, particles, and fields. Its strange features were interpreted as constraints on microscopic behaviour. Toward the end of that century, a shift occurred. Researchers began to treat quantum theory not only as a description of nature, but as a framework for processing information. Quantum information theory emerged from this shift. In 1984, Charles Bennett and Gilles Brassard introduced a protocol for secure communication known as BB84. Their idea was simple and profound. By encoding information in quantum states and exploiting the fact that measurement disturbs those states, two parties could detect the presence of an eavesdropper. Security would rest not on computational difficulty, but on the laws of physics. This marked a turning point. Quantum features such as superposition and entanglement were no longer viewed solely as conceptual puzzles. They became resources. The basic unit of quantum information is the qubit, short for quantum bit. A classical bit takes one of two definite values, 0 or 1. A qubit can exist in a superposition of both possibilities simultaneously. Mathematically, it is described by a state vector in a two-dimensional Hilbert space. In words, one may say that a qubit state is a linear combination of 0 and 1 with complex amplitudes. When measured in a particular basis, the probabilities of obtaining 0 or 1 are determined by the squares of those amplitudes, according to the Born rule. The power of qubits becomes more apparent when they are combined. Two classical bits can represent four distinct combinations, 00, 01, 10, or 11. Two qubits, by contrast, can exist in a superposition of all four combinations at once. More importantly, they can be entangled. Entanglement provides correlations that cannot be simulated efficiently by classical systems. It enables protocols such as quantum teleportation and superdense coding. In superdense coding, one can transmit two classical bits of information by sending a single qubit, provided that the communicating parties share an entangled pair beforehand. The resource character of entanglement invites quantification. How much entanglement does a given state contain? Can it be increased, decreased, or transformed? William Wouters addressed part of this question in the late 1990s by introducing a measure known as concurrence for pairs of qubits. Concurrence provides a numerical value between 0 and 1 that quantifies the degree of entanglement in a two-qubit state. A value of 0 corresponds to a separable state. A value of 1 corresponds to a maximally entangled state. Concurrence is derived from the density matrix of the two-qubit system through a specific mathematical procedure involving eigenvalues. Although the calculation can be technical, the conceptual purpose is straightforward. It assigns a clear number to how strongly the qubits are entangled. This quantification is essential because entanglement behaves differently from classical correlations. It cannot be increased by local operations and classical communication alone. If two parties share a weakly entangled state, they cannot simply apply local transformations to make it strongly entangled without additional resources. However, they can perform a process known as entanglement distillation. By starting with multiple copies of weakly entangled states and performing coordinated local operations combined with classical communication, they can sometimes extract a smaller number of states with higher entanglement. Entanglement distillation highlights the idea that entanglement is a consumable resource. It can be diluted, concentrated, or expended in communication tasks. This perspective has been formalized in what is known as resource theory. In resource theory, One defines a set of free operations and a set of valuable resources. For entanglement theory, local operations and classical communication are typically considered free operations. Entangled states are valuable resources because they enable tasks that free operations alone cannot accomplish. Researchers including Fernando Brandão have contributed to developing rigorous frameworks for understanding entanglement as a resource. These frameworks explore which transformations between quantum states are possible under specified constraints, and how entanglement measures behave under those transformations. One key principle in resource theory is monotonicity. A valid entanglement measure should not increase under local operations and classical communication. This ensures that entanglement cannot be created for free. In communication scenarios, entanglement enables protocols that would otherwise be impossible. Quantum teleportation, proposed by Charles Bennett and collaborators in 1993, allows the state of a qubit to be transferred from one location to another using a shared entangled pair and two classical bits of communication. The original qubit state is destroyed in the process, preserving the no-cloning theorem, which states that unknown quantum states cannot be copied perfectly. In computation, entanglement is widely believed to be a crucial ingredient in quantum speedup. Algorithms such as Shor's algorithm for integer factorization and Grover's algorithm for database search exploit superposition and interference. While debate continues about whether entanglement is strictly necessary for all quantum advantages, it is clear that highly entangled states often play a central role in powerful quantum computations. Experimental platforms ranging from superconducting qubits to trapped ions aim to create and maintain entangled states across dozens or even hundreds of qubits. These systems must carefully manage decoherence, since unwanted entanglement with the environment degrades useful entanglement within the computational register. Thus, entanglement functions as both a fragile and powerful asset. It enables tasks beyond classical reach, yet it must be protected from environmental interactions that disperse it. Quantum information theory reframes earlier foundational debates. Instead of asking only what entanglement means philosophically, it asks what entanglement can do operationally. This shift does not eliminate interpretational questions. Rather, it grounds them in practical capability. Entanglement is measurable, manipulable, and economically valuable in an informational sense. The transition from philosophical puzzle to engineered resource illustrates a broader theme in physics. Concepts that once appeared abstract and perplexing often become tools when understood precisely. Entanglement, once invoked as evidence of incompleteness or mystery, now underpins secure communication systems and the pursuit of quantum computers. In this context, information is not merely a metaphor. It is a physical quantity constrained by quantum laws. Entanglement determines how information is distributed across subsystems, how it can be concentrated, and how it can be harnessed. And as quantum information theory continues to evolve, it strengthens the view that entanglement is not an exotic anomaly at the margins of physics. It is a central currency in the economy of quantum processes, shaping both communication and computation at the most fundamental level. When entanglement first entered physics, it seemed like a philosophical inconvenience. It challenged locality, unsettled realism, and invited long debates. In the closing decades of the 20th century, it began to do something more practical. It started carrying messages. Quantum key distribution is one of the earliest and clearest examples. In 1991, Arthur Eckert proposed an entanglement-based protocol for secure communication. His scheme, often called the Eckert protocol, uses pairs of entangled particles shared between two distant parties. The idea is elegant. Suppose two partners share many pairs of entangled qubits prepared in a maximally entangled state. Each partner measures their qubit along randomly chosen directions. Because of entanglement, their measurement results will be correlated in ways that violate Bell inequalities. Those correlations serve two purposes at once. First, they generate a shared random key that can later be used for encryption. Second, they provide a built-in security test. If an eavesdropper attempts to intercept or measure the particles in transit, the delicate entanglement will be disturbed. The observed correlations will deviate from the expected Bell violation, alerting the legitimate users. Security is no longer based solely on computational assumptions. It rests on the structure of quantum correlations. This is not a thought experiment. Quantum key distribution systems have been implemented in laboratories and deployed in limited commercial networks. The challenge has always been distance, since photons travelling through optical fibres are absorbed or scattered over tens or hundreds of kilometres. To extend the range, researchers have turned to space. Jianwei Pan and his collaborators in China led the development of the Messius satellite, launched in 2016. Messius distributed entangled photon pairs between ground stations separated by more than 1,000 kilometres. These experiments demonstrated satellite-based entanglement distribution on a global scale. The correlations measured between distant stations were consistent with quantum predictions and suitable for secure key generation. The Earth itself became part of the experimental apparatus. Communication is only one side of the story. Computation presents another. In 1994, Peter Shor introduced an algorithm that startled the computational world. Shor's algorithm can factor large integers efficiently on a quantum computer. In classical computing, no efficient algorithm is known for factoring large numbers. The best classical methods require time that grows super-polynomially with input size. Shor showed that a quantum computer could perform this task in polynomial time. The significance is not merely academic. Many widely used cryptographic systems, including the RSA encryption scheme, rely on the practical difficulty of factoring large integers. A sufficiently powerful quantum computer running Shor's algorithm could, in principle, break such encryption. Shor's algorithm relies on quantum superposition and interference to perform a quantum Fourier transform efficiently. Entanglement plays a key role in correlating different parts of the computational register during the algorithm's execution. Without entanglement, the computational state would factor into independent pieces, and the full quantum advantage would not materialize. 2 years later, in 1996, Love Grover introduced another quantum algorithm. Grover's algorithm addresses a different problem: searching an unsorted database. Classically, searching through n items requires, on average, about n divided by 2 queries. Grover's algorithm can find a marked item in approximately the square root of n steps. This quadratic speedup is more modest than Shor's exponential improvement, yet it is still significant. For large databases, reducing the required number of steps from millions to thousands can matter. Grover's algorithm uses repeated amplitude amplification, a process that increases the probability amplitude of the desired solution while decreasing others. Entanglement often arises during these operations, binding qubits together in ways that classical bits cannot emulate. The exact role of entanglement in quantum speedup remains an active area of research. Some highly mixed quantum states exhibit limited entanglement, yet still provide certain advantages. In other contexts, strong multipartite entanglement appears essential. What is clear is that classical correlations alone cannot reproduce the full behavior of quantum algorithms. The tensor product structure of multi-qubit Hilbert space grows exponentially with the number of qubits. A system of 50 qubits has a state space dimension of 2 raised to the power 50, a number exceeding 1 quadrillion. Simulating such systems exactly on classical computers becomes rapidly infeasible. Entanglement allows quantum computers to explore this vast state space coherently. Interference patterns between amplitudes guide the computation toward desired outcomes. At the same time, entanglement is delicate. Interactions with the environment introduce decoherence, degrading the correlations necessary for computation. This is why quantum computing platforms, whether based on superconducting circuits, trapped ions or photonic systems, operate at extreme conditions. Superconducting qubits are often cooled to temperatures near absolute zero, measured in millikelvin. Trapped ions are isolated in vacuum chambers and manipulated with finely tuned laser pulses. Engineers strive to maintain coherence long enough to execute sequences of quantum gates. Error correction schemes have been developed to protect quantum information by encoding it across multiple physical qubits, using entanglement to detect and correct errors without measuring the encoded information directly. Thus, entanglement functions as both enabler and vulnerability. It grants computational and communicational power, yet it demands careful protection. The broader lesson is steady. Entanglement is not merely a curiosity about distant particles. It is a working ingredient in real devices. It underlies protocols that secure communication against eavesdroppers. It drives algorithms that challenge classical computational limits. It shapes the architecture of emerging technologies. And throughout these developments, the same principles remain intact. No faster than light signaling occurs. Relativistic causality holds. Bell inequalities are violated within quantum bounds. The mathematical structure of Hilbert space governs every step. The question of how distant things stay connected now acquires a practical dimension. Those connections are not just philosophical puzzles, they are operational tools. Entanglement, once debated in letters between Einstein and Born, now travels between laboratories and satellites. It links qubits in processors and photons across continents. What began as a conceptual challenge has become a technological resource, steadily reinforcing the conclusion that quantum connections are not anomalies in the margins of physics. They are central features of how information can be stored, transmitted, and processed in our universe. Entanglement is often introduced through photons, qubits, and carefully isolated laboratory systems. It can feel delicate, almost fragile, something that survives only in ultra-cold chambers and vacuum lines. Yet some of the most striking manifestations of entanglement occur not in isolation, but in bulk matter. Entire materials owe their properties to collective quantum states that cannot be reduced to independent particles. Superconductivity is one of the clearest examples. In 1957, John Bardeen, Leon Cooper, and Robert Schrieffer proposed what is now known as the Bardeen-Cooper-Schrieffer theory, often abbreviated as BCS theory. They explained how certain materials, when cooled below a critical temperature, conduct electricity with zero resistance. The key idea involves Cooper pairs. In a conventional metal, electrons repel one another due to their negative charge. However, under suitable conditions at low temperature, electrons near the Fermi surface can form bound pairs through interactions mediated by lattice vibrations, known as phonons. These Cooper pairs are not tightly bound like molecules. They are extended quantum objects that overlap with many others. Crucially, they form a coherent collective state. The wave function describing the superconducting ground state is not a product of independent electron states. It is a highly entangled many-body state. In this state, electrons move in correlated pairs across macroscopic distances. The phase of the collective wave function becomes coherent throughout the material. Because scattering processes that would normally cause resistance would require breaking these pairs, electrical resistance vanishes below the critical temperature. Superconductivity, therefore, is not just about electrons behaving nicely. It is about entanglement shaping a material's macroscopic behavior. Topological phases of matter reveal an even deeper role for entanglement. Xiaogang Wen and others have developed the concept of topological order to describe phases that cannot be characterized by conventional symmetry breaking. In such systems, the defining properties are encoded in global patterns of entanglement rather than local order parameters. The fractional quantum Hall effect, discovered experimentally in the 1980s, provides a vivid example. When electrons are confined to 2 dimensions and subjected to extremely strong magnetic fields at very low temperatures, they can form states with precisely quantized Hall conductance at fractional values. These fractional quantum Hall states cannot be explained by treating electrons as nearly independent particles. Instead, They arise from strongly correlated many body wave functions. The entanglement structure of these states gives rise to quasi-particles with fractional electric charge and exotic exchange statistics. The topology of the quantum state determines observable properties such as quantized conductance. The system's behavior depends not on microscopic details alone, but on global entanglement patterns. Entanglement entropy has become a powerful diagnostic tool in identifying such topological phases. In two-dimensional systems, the entanglement entropy between a region and its complement often follows an area law with a small correction term known as topological entanglement entropy. This correction encodes information about the underlying topological order. In these systems, entanglement is not an incidental correlation. It is the organizing principle of the phase. Even in more everyday materials, entanglement plays a quiet but pervasive role. Magnetism, for example, arises from quantum mechanical exchange interactions between electron spins. The Heisenberg model describes spin systems whose ground states can exhibit long-range entanglement. In certain regimes, quantum spin liquids emerge, where spins remain highly entangled without forming conventional magnetic order. Such phases defy classical expectations. They cannot be described by assigning definite spin directions to individual sites. Instead, the ground state is a superposition of many configurations, with entanglement linking distant regions. One might imagine that all of this remains confined to microscopic scales, yet experiments in optomechanics have begun to push entanglement toward larger systems. In optomechanical setups, tiny mechanical resonators, sometimes micrometer-scale mirrors or membranes, are coupled to electromagnetic fields inside cavities. By carefully controlling laser light and cooling techniques, researchers have generated entanglement between mechanical oscillators and optical modes. In some experiments, mechanical resonators containing billions of atoms have been placed into states exhibiting quantum coherence and entanglement. While these systems are still far from everyday objects like chairs or cats, they bridge the gap between microscopic and mesoscopic scales. Maintaining such states requires extreme isolation and precise control. Even slight thermal interactions can destroy coherence. Yet the fact that entanglement can be engineered in systems containing large numbers of particles demonstrates that quantum correlations are not confined to the smaller scales by principle. They are limited in practice by decoherence. These developments reinforce a broader theme. Entanglement is not merely a feature of isolated pairs, it is foundational to the properties of materials. The electrical resistance of a wire at low temperature, the quantist conductance of a two-dimensional electron gas, the emergence of exotic quasi-particles, and the coherent oscillations of mechanical resonators all trace back to collective quantum states. In classical thinking, material properties arise from local interactions between independent constituents. In quantum condensed matter physics, the collective wave function of many particles, often deeply entangled, determines the phase and behavior of the material. This shift in perspective mirrors earlier themes. Independence is not fundamental. Correlations shape reality. Materials that appear stable and classical at large scales are underpinned by quantum mechanical interactions at the microscopic level. In some phases, entanglement is subtle and largely hidden. In others, it becomes the defining feature. Superconductors carry currents without resistance because electrons pair in an entangled state. Topological materials exhibit robust properties because of global entanglement patterns. Quantum Hall systems display precise conductance plateaus due to collective correlations. The connection between distant parts of a material is not metaphorical, it is encoded in the many-body wave function, and so the story widens. Entanglement is not only a bridge between two photons or two qubits, it is the invisible architecture underlying entire phases of matter. The same principle that links distant particles in Bell tests also binds electrons into superconducting pairs and organizes topological states in quantum Hall systems. From the smallest scales to the properties of bulk materials, Entanglement remains woven into the fabric of physical reality. Despite the remarkable progress linking entanglement, geometry, and information, a complete theory of quantum gravity remains unfinished. The challenge is clear in outline. Quantum mechanics governs the very small. General relativity governs the very massive, and the structure of spacetime itself. Both are experimentally confirmed within their domains. Yet their mathematical frameworks are profoundly different. Quantum mechanics is built on Hilbert spaces, linear operators, and probabilistic amplitudes. General relativity describes a smooth spacetime manifold whose curvature responds to energy and momentum. Reconciling these pictures into a single coherent framework has occupied theoretical physics for decades. One major approach is loop quantum gravity, developed in part by Abhay Ashtekar and collaborators beginning in the 1980s. Loop quantum gravity reformulates general relativity using new variables, known as Ashtekar variables, which recast the gravitational field in terms resembling gauge theory. In this framework, spacetime geometry itself becomes quantized. Instead of a smooth continuum, area and volume operators have discrete spectra. Space is described by spin networks, graphs whose edges and nodes carry quantum numbers. These spin networks represent quantum states of geometry. The fundamental idea is that geometry is not infinitely divisible. At extremely small scales, on the order of the Planck length, roughly 1.6 times 10 to the minus 35 meters, space may consist of discrete quanta. The Planck area and Planck volume emerge as natural scales in this theory. Entanglement plays a role here as well. Spin network states encode relational information between nodes. The connectivity of the graph determines geometric relations. In this picture, geometry arises from combinatorial and algebraic structures, rather than from a smooth background manifold. Loop quantum gravity remains a mathematically consistent and actively researched approach. It has had partial success in deriving black hole entropy, in agreement with the Bekenstein-Hawking area law under certain assumptions. However, it has not yet produced experimentally testable predictions distinguishing it clearly from other approaches. Another proposal is causal set theory, developed by Raphael Sorkin and colleagues. Causal set theory begins from a different starting point. It posits that spacetime is fundamentally discrete, and that its basic structure is a partially ordered set of events connected by causal relations. In this view, spacetime is not a continuous manifold, but a collection of discrete elements ordered by causality. The number of elements corresponds to spacetime volume, and the ordering encodes causal structure. Geometry, including curvature, would emerge statistically from the distribution of these elements. Causal set theory preserves the central role of causality from general relativity, while introducing discreteness at the most fundamental level. It avoids assuming a background geometry, and instead builds spacetime from elementary events. Like loop quantum gravity, causal set theory remains under development. It offers conceptual clarity about discreteness and causality, yet connecting it to established low-energy physics and deriving concrete experimental signatures remains challenging. Emergent spacetime hypotheses take a broader perspective. Inspired by holography and entanglement entropy results, some researchers propose that spacetime itself emerges from quantum entanglement, or from more abstract informational structures. In these views, spacetime is not fundamental. It is a large-scale approximation arising from deeper degrees of freedom. Entanglement patterns determine connectivity. Geometry reflects information flow. This idea aligns with earlier discussions of the anti-de Sitter/conformal field theory correspondence and tensor network models. However, extending these insights beyond idealized anti-de Sitter settings to our expanding universe with a small positive cosmological constant remains unresolved. All these approaches face significant experimental limitations. Quantum gravity effects are expected to become significant at the Planck scale. The Planck energy corresponds to approximately 10 to the 19 giga electron volts. For comparison, The Large Hadron Collider at CERN reaches energies on the order of 10 to the 4 giga-electron volts. The gap spans 15 orders of magnitude. Directly probing Planck-scale physics with particle accelerators is currently beyond technological reach. Some researchers search for indirect signatures. Possible avenues include tiny deviations in the propagation of high-energy cosmic rays, modifications of black hole evaporation, or imprints in the cosmic microwave background. So far, no unambiguous experimental evidence for quantum gravity has been confirmed. Conceptual tensions remain as well. One major tension concerns the problem of time. In canonical approaches to quantum gravity, such as loop quantum gravity, the Wheeler-DeWitt equation describing the quantum state of the universe lacks an explicit time parameter. This leads to deep questions about how temporal evolution emerges from a fundamentally timeless formalism. Another tension involves the black hole information paradox. If black holes evaporate completely through Hawking radiation, what happens to the information about the matter that formed them? Unitarity in quantum mechanics demands information conservation. Early semi-classical calculations suggested information loss. More recent developments, including holographic insights and calculations of so-called page curves, indicate that information may be preserved in subtle correlations within Hawking radiation. Yet a complete consensus remains elusive. There is also the challenge of background independence. General relativity treats space-time geometry as dynamical. Many quantum field theories, by contrast, are formulated on fixed backgrounds. A fully satisfactory quantum gravity theory should ideally avoid presupposing a fixed space-time stage. Each proposed framework addresses some aspects of these tensions while leaving others open. The landscape is therefore one of active exploration rather than settled doctrine. Loop quantum gravity quantizes geometry directly. Causal set theory discretizes space-time events. Holographic approaches suggest space-time emerges from entanglement. String theory, though not detailed here, introduces additional dimensions and extended objects. No approach has yet achieved comprehensive experimental confirmation. This uncertainty is not a failure. It reflects the extraordinary difficulty of unifying two of the most successful theories in physics. Both quantum mechanics and general relativity have been tested with extraordinary precision in their respective domains. Bridging them requires navigating scales and regimes far removed from everyday experience. Entanglement remains central in many of these efforts. Whether through holographic dualities, spin networks, or entanglement entropy calculations, quantum correlations appear deeply intertwined with geometry. The unresolved conceptual tensions serve as reminders that the story is not complete. The connections between information, space-time, and gravity are compelling but not yet fully understood. What is clear is that entanglement is not an isolated phenomenon confined to laboratory experiments. It reaches into the structure of matter, the emergence of classical reality, and the fabric of space-time itself. The final answers about quantum gravity remain beyond our current experimental horizon, yet the questions themselves continue to refine our understanding of how distant things might stay connected at the deepest levels of physical law. How can distant things stay connected? After all the equations, experiments, interpretations, and speculative bridges between space-time regions, the question returns in its simplest form. Two systems move apart. Kilometers may separate them. Light may take measurable time to travel between them. Yet when measurements are performed, correlations appear that no classical local model can reproduce. The answer is not that a hidden signal flashes across space at superluminal speed. The no-signaling theorem ensures that no controllable information travels faster than light. Special relativity, established in 1905 and tested repeatedly through particle physics and satellite navigation, remains intact. The answer is more structural. Entangled systems share a single quantum state. That state is described mathematically in a Hilbert space formed by the tensor product of the subsystems. If the state cannot be factorized into independent parts, then the systems are not independent in the classical sense, even if they are spatially separated. The connection lies in the joint structure. When a pair of particles is prepared in a singlet spin state, for example, the total spin is defined even though the individual spins are not. The state encodes relational information. Measuring one particle reveals something about the other, because both are described by a single, inseparable quantum state. Nothing is transmitted at the moment of measurement. Instead, the correlation was encoded at preparation. John Bell's theorem in 1964 demonstrated that no theory based on local hidden variables can reproduce the correlations predicted by quantum mechanics. The Clauser-Horn-Schiemeny-Holt inequality quantified that limit. Experiments by Alain Aspect in the early 1980s, followed by increasingly refined tests by Anton Zeilinger, Ronald Hansen, and teams at the National Institute of Standards and Technology, consistently observed violations of the classical bound. The measured values approach the quantum limit of approximately 2.828, Zerelson's bound. They do not exceed it. The data align with quantum predictions and reject local realism in the EPR sense. This empirical confirmation has accumulated over decades, across laboratories, across continents, and even through satellite-based experiments led by Jean-Wei Pan. The conclusion is steady and robust. Entanglement is real. The structural perspective clarifies why this does not contradict relativity. The reduced density matrix describing one subsystem remains unchanged by measurement choices performed on the other. Local statistics are unaffected. Correlations appear only when results are compared through ordinary communication. Thus, entanglement reflects shared structure, not exchange signals. The informational perspective adds another layer. Entanglement distributes information across subsystems. The von Neumann entropy of a subsystem increases when it becomes entangled with its partner. Information about the whole is not stored locally, it resides in correlations. In quantum information theory, entanglement becomes a resource. It enables quantum key distribution, teleportation, and computational speed-up. It can be quantified through measures such as concurrence. It can be distilled and manipulated under the constraints of local operations and classical communication. From this viewpoint, distant systems remain connected because they participate in a single, informational structure. The classical idea that each subsystem carries its own, complete set of properties is replaced by a relational description. The geometric perspective extends the idea further. In quantum field theory, even the vacuum is entangled across space-like regions. The Ray-Schlieder theorem reveals that local operations can approximate global states because the vacuum itself is highly correlated. In holographic dualities, entanglement entropy in a boundary theory corresponds to geometric surfaces in a higher dimensional spacetime. The Ryu-Takayanagi formula ties entropy to area. The ER equals EPR conjecture suggests that entanglement may correspond to geometric connectivity, such as Einstein-Rosen bridges. These developments do not imply that laboratory particles are joined by traversable tunnels. They suggest that connectivity in quantum states may have geometric interpretation at deeper levels of description. Across structural, informational, and geometric viewpoints, a common theme emerges. Classical separability is not fundamental. In classical mechanics, the state of a composite system is simply the collection of the states of its parts. In quantum mechanics, the state of the whole may contain correlations that are irreducible to individual descriptions. Independence becomes approximate. Decoherence explains why classical independence appears in everyday life. Entanglement with the environment suppresses interference between macroscopically distinct states. Pointer states become stable. Redundant encoding of information through quantum Darwinism produces objective classical outcomes. At large scales, objects behave as if they possess independent properties. That behavior is real and reliable. It is simply emergent rather than fundamental. The tension that troubled Einstein was not about faster-than-light signaling alone. It was about the idea that distant systems should have independent real states. Quantum mechanics revises that assumption. It does so without abandoning empirical discipline. The predictions are precise, the correlations are measured, the limits are defined, the mathematics is coherent. How can distant things stay connected? Because at the quantum level, distance does not guarantee independence. Systems that have interacted may share a joint state that persists even when they move apart. The connection is encoded in that state. The world is not composed of isolated fragments stitched together only by local forces. It is structured by patterns of correlation that sometimes extend beyond classical boundaries. This does not dissolve causality. It does not permit arbitrary influence across space. It reframes the notion of what it means to be separate. The classical picture of distinct objects with intrinsic properties remains extraordinarily useful at everyday scales. It emerges from decoherence and environmental entanglement. But beneath that layer lies a deeper description in which relations precede isolated attributes. Entanglement is not an anomaly, it is a window into that deeper structure. Distant things remain connected because in certain states they were never fully separate to begin with. And that conclusion, supported by decades of experiment and guided by consistent mathematics, invites a quieter shift in perspective. Perhaps connection is not something that travels across space. Perhaps it is something that space itself reflects. Quantum entanglement expresses something precise and radical about physical law. It tells us that the state of a composite system is not always reducible to the states of its parts. Non-separability is not a philosophical add-on. It is written directly into the mathematical structure of quantum theory through the tensor product of Hilbert spaces and the existence of non-factorizable states. This feature has been tested repeatedly. From John Bell's theorem in 1964 to the experiments of Alain Aspect in the early 1980s, and through increasingly refined tests by Anton Zeilinger, Ronald Hansen and research groups at the National Institute of Standards and Technology, the empirical verdict has been consistent. Nature violates classical inequalities. Quantum predictions are confirmed within experimental precision. No faster than light signaling is observed. Relativistic causality remains intact. Theory, experiment, and information structure align. The formalism of quantum mechanics predicts entanglement. Laboratory measurements verify it. Quantum information theory quantifies and exploits it. Quantum field theory embeds it into the vacuum itself. Holographic dualities suggest it may even underpin aspects of geometry. Across these domains, the same principle appears. The whole can possess structure that no list of independent parts can fully capture. At the same time, caution is essential. Not every speculative extension has been confirmed. Proposals in quantum gravity, including holographic conjectures and emergent spacetime hypotheses, remain areas of active research. They are mathematically motivated and internally consistent in specific models, but direct experimental evidence at Planck scale energies is beyond current technological reach. The frontier is real, and so are its limits. What is not uncertain is the core phenomenon. Entanglement is measured, engineered, and harnessed. It secures communication, it shapes materials, it defines correlations that classical theories cannot reproduce. Classical separability, so intuitive and reliable in daily life, emerges from decoherence and environmental interactions. It is an effective description, not the deepest layer. Beneath it lies a relational structure in which systems can share a joint state across space without exchanging signals at the moment of measurement.